Hello everyone, welcome back to Dr. A classes, where we explore geology, hydrology, groundwater, and beyond. In today's session, we'll work through lesson 6, that is numerical exercise on precipitation. Let us begin with our first problem. Problem first is estimating mean rainfall and additional rain gauge stations. A catchment with 7 rain gauge stations has recorded the following annual rainfall amounts. We need to determine how many additional rain gauges are required to estimate the mean rainfall within a 5% error margin. Let us see how to solve it. Solution to the problem 1. From the precipitation data of a catchment having 7 rain gauge stations, the following statistics were obtained. Standard deviation equals 22.545, mean rainfall equals 130.43, and the coefficient of variation equals 17.286 using the given formula. We'll use the formula n equals C subscript V divided by epsilon squared, where n is required number of rain gauge stations, C subscript V is coefficient of variation of rainfall in decimals form, epsilon equals permissible error in the mean rainfall, also in decimal form. Substituting the values, n equals 17.286 divided by 5 squared, which gives approximately 11.95. Rounding up, we need 12 stations in total. Since we already have 7, we require 5 additional rain gauge stations to achieve the desired data. Problem 2. Estimating missing rainfall data. In the next problem, one of the rain gauges, station T, was not working during a storm. We'll estimate the missing rainfall using the normal ratio method. Let us calculate missing value. Solution to the problem 2. Using the given data and the normal ratio formula, we find that the rainfall at station T is approximately 12.86 centimeters. So we can safely assume that during this storm, station T received about 12.9 centimeters of rainfall. Problem 3. Testing consistency of the rainfall data. In this problem, we are asked to test the consistency of the rainfall data for station A using the double mass curve method. The data covers 13 years and will check if there is any change in the rainfall pattern or regime. The graph shows the double mass curve for rainfall data from 1946 to 1958. The blue line represents the original data and the green line shows the adjusted data. A clear change in slope occurs around 1955, shown by the red dashed line indicating inconsistency likely due to a station shift or instrument change. The table shows the rainfall data from 1946 to 1958. The slope values before 1955 are around 1.19 and after 1955 they drop to 0.98, marking the year of regime change. To correct the inconsistency, we use the post-1955 slope, that is 0.98, as the baseline and scale the earlier data using the slope ratio formula. PA adjusted is equal to PA into 0.98 by 1.19. Applying this correction brings the pre-1955 data in line with the later consistent trend. After adjustment, the double mass curve becomes a straight line, proving that the rainfall data are now homogeneous and reliable. By applying the slope ratio correction, the adjusted data now follow a uniform trend, and the mean annual precipitation for station A is about 147 millimeters. Therefore, we can say that after 1955, the rainfall record becomes consistent and reliable for further hydrological analysis. Problem 4. Estimation of average precipitation, isohydral method. Let us move on to problem 4. Estimating the average precipitation over a 600 square kilometer catchment using the isohydral method. The isohydral intervals and corresponding inter-isohydral areas are provided. Solution to the problem 4. First we find the mean rainfall between each pair of isohydrates and then multiply each by its respective area. After summing all the products, we get 4443.5 centimeters square kilometer. Dividing by the total area of 600 square kilometers, the average depth of precipitation comes out to be 7.41 centimeters. Problem 5. Thesan polygon method. In our final problem, we'll determine the mean aerial precipitation using the Thesan polygon method. The rainfall and corresponding polygon areas for 5 gauges are given. Let us apply the area weighted formula. Solution to the problem 5. The diagram shows 5 rain gauge stations P1, P2, P3, P4 and P5, each recording rainfall between 10.2 and 13.2 centimeters. The dashed lines represent the Thesan polygon which divide the catchment so that each station's polygon covers the area closest to it. These polygon areas will be used to assign area weights to each station's rainfall, allowing us to calculate the weighted average precipitation for the entire catchment. To find the mean aerial precipitation, we multiply each rainfall value by its respective area as shown in the last column. The total of all Pi and Ai values is 5799.0 centimeters square kilometer and the total catchment area is 500 square kilometers. Substituting these values in Thesan area weighted formula, we get mean precipitation is equal to summation Pi into Ai by summation Ai, that is equal to 5799 divided by 500, which is 11.6 centimeters. So the mean aerial precipitation over the catchment is approximately 11.6 centimeters. Self-assessment numerical problems. Now it's your turn to practice. Try solving these self-assessment problems to test your understanding of rainfall measurement, estimation, and data consistency. You can pause the video here and attempt each question before checking your answers. That is all for today's lesson. Numerical exercise on precipitation. I hope you found it helpful and easy to follow. Don't forget to like, share and subscribe Dr. A classes for more lessons on hydrology, groundwater, engineering geology and civil engineering fundamentals. Thank you for watching and see you in the next class.